So welcome to my third lecture today. This is going to be mostly about SPH, and this is actually a little fun calculation I did a few weeks ago with SPH, with this actually gadget. So it can do a bit of fancy rendering, also things that take place here on Earth. This is supposed to be sort of a lava lamp where you have two fluids that don't mix, they're immiscible, and there's a heating zone in the bottom and a cooling zone in the top, and so that sets this fluid basically in motion via usual Buoyant's forces. And this is actually something that you can simulate with SPH quite nicely, because there you can actually achieve things like surface tension and prevent fluids from mixing quite easily, and I'll discuss this a bit more in my fourth lecture. And actually the high viscosity that you have in SPH compared to mesh codes is in a problem like this kind of an advantage. But this is, of course, just for fun. Now today in my third lecture, I want first spend some fair amount of time to actually finish off what I started last time, to talk about basic technical aspects of parallelization in gravity calculations, because I think this is an area which is often overlooked. It's taken for granted that you can parallelize algorithms. But this is actually a real challenge, especially for gravity, which is a long-range force, and for strongly clustered simulations. They're very inhomogeneous, and their calculation demands very strongly throughout a computational volume. And that makes it very hard to parallelize. And so I'll tell you a bit about my own experiences with some attempts to, say, improve parallelization in my own codes. And this is just meant to raise some of the issues and tell you about some of the buzzwords to encourage some of you to come up with new ideas. Because I think that's really needed in the future if you have ever larger computers and if you want to put them at work on these problems. And then, of course, I'll finally move over to smooth particle hydrodynamics, and the rest of my lectures will be more concerned with issues of hydrodynamics and in the particle context, which is sort of a poor man's hydrodynamics in many respects. So I also will address some of the limitations this approach has, because it's very important to be aware of them. So parallel computing. Last time I told you about the need to decompose a simulation onto distributed memory systems. So we make, say, for example, a spatial domain decomposition. And then there are techniques like the space filling curve or other techniques to do this in practice. But generally, you want to cut your domain such that roughly the same calculational work is assigned to each of the domains. Right? That's the principle that you obviously have to fulfill. So you want to make these pieces that you obtain by, say, cutting a space filling curve, these 5 domains. You want to cut them such that the particle load is maybe roughly balanced, but that's not the only criterion. Maybe each of these particles here has a different calculational cost for the gravity force. If it's more strongly clustered, it will have a bit higher cost. Also, then its time steps will be shorter, so the frequency with which the force has to be recalculated will be higher. So you need to devise some scheme that measures that sort of calculational cost of each particle. And then you want to cut your domain such that the sum of the costs of all the particles in the domains is equal. So that's sort of the goal. And why do you want to do this? Well, it's kind of obvious. You want to give each of the processes an equal amount of work so that they are done at the same time, and that you can actually realize a large scale-up. Now I want to go through some of the problems that you then come up with in practice, because it's actually usually not totally trivial to achieve that balance of work, at least not in collisionless dynamics. In strongly clustered calculations, it is easier, I would say, if you have, say, a Cartesian grid with nearly homogeneous density or so, and you can just hand out equal numbers of cells to each process. Then it's quite simple. But that's not the case really in structure formation calculations. So what type of problems do you actually encounter in practice? First of all, and the problems basically cause losses. So your code doesn't run as fast as you want, and it's actually often not easy to remedy this problem. And here I go through the reasons why this is. So the first source of losses basically stems from incomplete parallelization. So if you have any given code and you want to port it to a parallel computer, then you might concentrate on the most, calculation-intensive part first. You parallelize that. Then you're left maybe with some part in the code that is still serial. And you think initially maybe, oh, that should be fine, it's not dominant. But there is something that's called Amdahl's law. So if you have any small fraction of residual code left, say 5%, then that immediately limits the maximum speedup that you can achieve. It's going to be a factor of 20, because that 5% will still stay around all the time, right? So that shows you immediately that to reach scalability to, say, 10 to the 5 processors, you have to suppress the fraction of serial leftover code to 10 to the minus 5, basically. And that's not that easy. You have parallelization overhead. So when you change your algorithm to make it massively parallel for distributed memory systems, you usually have to rewrite it, and there will be additional code required to deal with bookkeeping. For example, informing you where certain parts of the calculation lie and so on. You have to write this additional code, and sometimes there are non-trivial calculations involved, so this is some extra work you have to do. Then, of course, you have times that are required to actually send data around, communication times. There's certain bandwidth on the network, and it will take some time to send messages around, and that's often quite expensive. So if you go shopping for a supercomputer, then you want to invest in your network, and you find out that the better the bandwidth is, the price is going to rise very steeply with it. But that will cut down your communication times. Now, fortunately, in this area, if you have a computation-intense code, often the raw bandwidth is sometimes, at least on the modern hardware, is often not a huge problem. There are also other issues like latency, the time it takes to actually establish a connection. There's some wait time involved, and then that factors in when you have a granularity in your communication pattern. So sending around lots of small messages costs you extra, because each time you have to start up the communication protocols. There's latency time in that. But bandwidth is generally more important. But the most serious loss, at least in my experience with the codes I work with in parallelization, are plain wait times that arise due to workload imbalances. Because that happens because you simply didn't manage perfectly well to distribute the workload evenly. And what then happens is that the CPU that is fastest, that finishes first, will then just idling until the slowest one has also finished. So it's always the slowest processor that sets the pace. And that can ruin a lot of performance and has a huge leverage. If you run something on 2,000 processors, only one of them is a factor of 2 slower. Well, all the other 2,000 processors, they will just sit around half of the time and do nothing. Right? So that's very important to realize. Of course, when you talk about parallelization, there are also other issues that were already explained early in the week: strong scaling and weak scaling. So ideally, in strong scaling, you would like to just run a given problem faster by increasing the number of CPUs. And the speed up that you then obtain, if that's basically proportional to the number of CPUs you put on the problem, then you're in the strong scaling regime. And that's most difficult to achieve, and that's the best of that you can have, right? If you have a strong scaling code, you're really in business. You can make things go faster. But most of the time, you will also, at least at some level, increase problem sizes to go to very large computers. And weak scaling kind of means then when you increase not only the number of CPUs, but also the problem size, and then you manage then to keep the parallelization losses small, then you're in the weak scaling regime. And say Gadget is hopeless in the strong scaling. I'll show you some examples. It goes only over a certain range, but for certain problems, it's reasonably well weakly scaling. And one important lesson also from practical experience is that it usually doesn't make sense to use a large number of processors on a tiny problem size. Right? I get lots of people sending me email and complaining, look, code is going slow. I have this 10,000 particle galaxy simulation. I run it on 512 cores. Why is it not going 512 times faster? Well, if you have only a handful of particles per processor, you're not going to get a huge speed up. And it's fairly obvious. But you should always keep this in mind. If you have a large computer, you're better off having a large problem as well. That makes it a lot easier. Okay, so this is once more about Amdahl's law. Example, if you have 5% serial stuff left, speed up is at most a factor of 20, no matter how many processes are used. And there's a nice quote here from Tom Gargill from Bell Labs about parallelization, basically. The first 90% of the code accounts for the first 90% of the code development time. The remaining 10% account for the other 90%. So what he means is that it's getting harder and harder to squeeze out these remaining residual serial fractions in the code. So this is sort of what's achieved, say, with a code like Gadget 3 in practice. This is a strong scaling test on different architectures, 256 cube particles. And then you see that the time for a full time step is sort of dropping if you put more processors, but it's dropping eventually. Here for the strongly clustered case, this is redshift 0. This is at high redshift. In the initial condition, it looks better because the particle load is reasonably homogeneous. At late times, you see losses here at already 128 processors. You are basically slower by a factor of 2 compared to the ideal perfect scaling. And the code still gets fast at this point, so it's still not bad, and you would still run in such a mode in practice, but it's still problematic. But this was for a cosmological structure formation simulation. If you have a more demanding problem, for example, a measles small individual galaxy or galaxy collision simulation, here just run with 8 different numbers of processors, 1 processor, 2, 3, 4, 5, 6, 7 to 8. And sort of this rectangular area and the different colors here show you over different time steps what the code is actually doing, where the time is spent. And the most time-consuming part here are the gravitational tree walks. This is the black area in these rectangles. So most of the time, the CPUs calculate away on the gravitational tree walk. So that's correct. That's what should happen. Occasionally, you see other things, particle stepping or domain decomposition and so on. And then also this sort of pattern here stems from the individual time stepping in the code. But then you see another interesting thing. There's some white area here on top. This is basically essentially idle time. Due to communication rates and workload imbalances. And you see if you go up to more and more processes, this white area here gets larger in a fractional sense. And the thing gets faster, so this is for the same number of time steps. You finished still earlier from 7 to 8 processes, but the losses get ever larger. And there will be a point where this runs out of steam and you can't scale anymore. And so now I want to basically talk a little bit about the problems in trying to improve on this situation, trying to get rid of some of these wait times. And why do they actually occur and where in the code? Well, I described to you the way how the gravitational tree is split up in the Gadget code at least, but other codes work in principle similarly. And then Gadget has a strategy that the force for particles will be first of all calculated with the local tree, but then that might not be sufficient. There are, even though there's a top-level tree, sometimes you need to open tree nodes that are on remote processes, and instead of importing these tree nodes, actually Gadget turns this around and it sends the particle to another processor, lets it calculate the residual partial force and the results coming back. And that means that you also have to do this service for other processors, and so if you're an individual processor, you will first calculate forces for local particles and then do some forces as a service for imported particles, and you'll send back the results. So these are the 2 phases of this algorithm of a gravitational tree walk. And what you want to balance in the code is the total elapsed time for this gravitational tree walk. So all the processors should have an equal amount of time here. So suppose now you have 8 processors, and you're making your domain decomposition such that these 2 times are equal, then you might end up with a situation like this. So these are the 8 processes, and the sum of these 2 parts is almost equal. There are some little fluctuations in here which will be our lost times. And this looks great. I mean, there are a couple percent losses here, but actually what really happens is that once you're done with your local particles, you have to communicate, right? You want to send out the things that your particles to other processes, and you need to request information from other processes. And these communication steps are very often happening in a synchronized way. So what really happens is that in the first communication step, you're effectively waiting for the slowest processor. And when everybody has arrived here, you can finish the data exchange. And then they start the second part now in a synchronous way. And then again, at the end of the second cycle, you wait for the slowest processor. And now suddenly you have accumulated huge amounts of wait times, all this orange stuff here, which is all loss. So that's pretty bad, right? So you have additional constraint. You not only want to have the total time balanced, but also the meter times. And what actually happens is basically on top of this thing, you then have the actual communication times also. As I said, they are usually small, so this gray area is not so bad. But that's then, why a parallel code will not speed up a lot sometimes, because it's this nasty issue of workload imbalance. Now, are there strategies to get around this? Well, I've worked on this quite a bit and tried lots of things, and most of them didn't work very well. So one thing, for example, to try to get around of this is to try to eliminate the need for synchronous communication. So if you do MPI, all the basic communication patterns, they are all synchronous. That means that the sender and the receiver simultaneously need to send a request to talk to each other, and whoever does it first waits until the other side also responds. Right? So that's the synchronous mode. But there are now in the MPI2 standard also other ways to do it. For example, one-sided communication. So here the idea is that you basically only one of the sides can initiate the communication call, and the other side doesn't even have to call a function call. And that way, you might think you can get rid of this synchronous point in the middle. This is for various reasons pretty complicated, because it's actually not true that it's in the MPI2 standard a complete one-sided protocol. You actually have the other side must also participate in this in some fashion. And it, in fact, the progress on such communications will rely on MPI calls also in the target. So it basically nothing really happens usually if the target does not enter an MPI function as well. And then there are also asynchronous communication calls. That's yet something different from one-sided communication. Here, basically, unlike in the ordinary MPI calls, you want to send, for example, a message, and an asynchronous send would just return immediately from the sender. So you should, for example, say, it's like sending off some ordinary mail to the post office. You go and you deliver it, and then you return home. And the message will be arriving sometime later at the receiver, right? And when the receiver picks it up, you don't care, right? That's sort of asynchronous communication. And maybe this is a technique to get around some of these problems. But don't want to discuss this. So this is sort of the one version of Gadget where a completely one-sided asynchronous protocol was implemented, and communication and computation were tried to be overlapped. This is also something that, in principle, some of the modern hardware can do, that the MPI communication is sort of running in the background while the processor still calculates away. That's always in the advertisement of these libraries and of these big computer vendors. I've never really found that this to work in practice, though. I don't know why, whether it was my mistake or not. But in principle, this is sort of the acute ideas for the future that you might want to try out at some point. Final caution, he wrote also about the asynchronous send after having invested a lot of time in implementing this in a code, and eventually found out why it didn't really succeed particularly well, is because the asynchronous sends and receives, they don't usually work the way you actually expect, right? So what I expected how this might work is sort of depicted in this ideal communication pattern here. So the idea is that you have two processors doing some calculations and exchanging some messages. In particular, this blue rectangle here is the company calculation. And here you have the CPU B is at some point finished and needs to send something to processor A. And with an asynchronous MPI call, the idea would be, okay, you deliver this message here, and then you send it, and CPU B can do some useful stuff again. And when CPU A is at some point finished and is now just right and ready to pick up this message there. And so you have no wait times here, right? And the calculations can proceed with maximum speed. And that's what I wanted to achieve. And unfortunately, what really happens in practice is basically this on most MPI libraries. So what happens here? basically, it's true that the asynchronous MPI call of B will return immediately, and so B can continue to calculations. But actually, when an A is now ready, and nothing really happened here, it's just like the MPI library stored in some message list. Oh, there's something to be sent to A. But A is not listening at this point. It can't do anything. And the MPI library usually don't interrupt ongoing calculations on the main processor. So basically nothing happens at this point. It's just here in the message list. And so B now does calculations, and A is at some point finished and is ready to pick up the message. But the message is still not picked up because B is not ready to send. It's doing calculations at this point. So then A will wait until B the next time calls the MPI library, and then this thing is finally exchanged. So and that's basically what on almost all the MPI libraries I tried, this is basically what happens. Unfortunately, and at this point, funny enough, it becomes again better if you do this synchronously. Because if you, here in B, if B now waits until A is also ready to receive the message, then B just waits this amount, and this wait is actually shorter than this. So this is just some of the subtleties why this MPI parallel programming is so hard in general, why you can have so many sources of losses. Sorry? No, the message, that's what happens here, right? That's why B returns. The message is buffered, but it's buffered on B. Okay. So all that happens is that you have your application memory space somewhere, you send it off. Okay, you can make a buffered call, then the MPI library copies it into its memory, but that is on B. That's the problem. So the message is still on B.
Volker, post the receive before you post the send. That's what we do.
Yeah, that's true. That's what I'm also doing. Yes, if yes, you post but that is helpful because but still, so you can post the receive here, right? But the transaction will still not happen at this point. Normally, it depends on the MPI library because A is, if the MPI library can't make an interrupt here or doesn't have DMA access to the memory of A, nothing's going to happen. It requires participation of A, finally. Yeah, it does depend on the library. The good libraries will finally do this at some point. Yeah, or some do maybe, but it's not poor. Unfortunately, even when MPI came out, I thought this is finally solved, but it's on many libraries it doesn't work, and even on good libraries from IBM as well, depending on the system. But yeah, I mean, I think this is maybe going to, so basically what the thing why this doesn't work so well is, in practice, is that you have to have the IBM MPI library needs to be able to basically deposit something in the target's memory without this processor being participating. So or there must be a possibility, say, an interrupt or something. Otherwise, it's not working. And the MPI libraries don't do that normally. So other strategies to improve the workload balance. So what I've implemented in Gadget 3 is basically to get around the scaling problem on big isolated systems that I yet again changed a bit the domain decomposition. Very simple idea. So just to remind you again of what this was. So in Gadget 1, I used a so-called orthogonal recursive bisection for cutting the domains. Here you cut along different spatial directions alternatingly, and that produces relatively extended domains here. And again, the decomposition, especially of the central region, where the time steps are shortest, is suboptimal because it only goes to few of the processor elements. And with the space filling curve, you do a bit better. This is, for example, what happens in Gadget 2 here. With such an isolated galaxy, you get sort of various pieces, and they are not necessarily of rectangular shape, which allows you to achieve better workload balance. And this is sort of what in Gadget 3 is done. So the whole thing here is decomposed in many more patches at the cost of additional communication. And that actually with that scheme, you can workload balance the calculation much better and also memory balance it at the same time. So the idea basically here is that I've implemented a scheme where I'm not only decomposing the space field curve in, say, 4 pieces, if I have 4 cores, but in multiple pieces. And these pieces are then, again, sent out to the different processes, but each process now gets a piece from different regions of the calculation. And that way you can balance the work and the memory balance basically simultaneously, but you have to communicate more. And then the question is what wins out. But for many problems, actually, this second strategy wins out. And because workload imbalances are so terribly bad, if you can avoid them, you can do a lot of stupid extra things, but you're scaling better. So that's, for example, on this problem of a galaxy, how now the scalability works between these 2 codes. You see here it kind of nosedives already at 100 CPUs, and that keeps going a bit longer. That, of course, just to mention this, for the 3 PM algorithm, this decomposition is very different from the one you need for the Fourier transform, which is a slab decomposition here, right? And this is pretty elaborate to efficiently swap between these 2 things in a way that minimizes the communication and still keeps the workload balance and memory balance in both parts of this calculation. So if you are interested in how to do this, please feel free to talk to me. And then finally, final point I want to make is, of course, it's not only CUDA that's exciting these days and what's developing, but we all know that there's this trend to multi-core processors, or ordinary processors having multi-cores. That basically means you have suddenly a shared memory machine even in your laptop with multiple cores. And exploiting the shared memory is a very good way to reduce basically the workload imbalance losses, because it allows you to reduce the number of MPI tasks. And in particular, you can eliminate the workload imbalance losses that you have basically between the different MPI tasks on the same chip, on the same CPU. For example, you have now quite commonly quad-core CPUs, but of course there are more core numbers are coming up. And if you additionally run an MPI code like H200, you would put an MPI task on all of these cores which are on the same chip. And they can, in principle, exploit shared memory. And then again, what happens is that in a time step, you're going to be limited by the slowest of these tasks, right? Maybe the workload balance here was really bad. This one process takes a long time, and you see all these access time is all idle time. But with shared memory, it's much easier. You can essentially completely eliminate the workload imbalance loss within the same processor if you put only one MPI task on this CPU, and you utilize the other cores with threads. And that you can do with either OpenMP as the simplest parallelization scheme that you then can put it at use for that, or you actually explicitly program the threads. That's also not so complicated. It's a bit more flexible with something like POSIX threads. And then you have a situation where you have no or effectively no workload imbalance at the chip level. And suddenly the number of MPI tasks you have is a factor 4 lower, and sort of your scalability limit is effectively a factor 4 higher. And I think the future for off-the-shelf simulation codes will be very much be given by mixed MPI OpenMP codes. That's probably the best you can do. And there I would recommend to write the MPI code first and only add the OpenMP stuff later on, or the thread stuff, because the other way around is you will not get an efficient MPI parallelizable algorithm. So sort of this shameless advertisement for Gadget 3, I basically want to skip. I just want to say some of these things I discussed are implemented in a new version of Gadget, which is in many ways quite a bit better, well, very much better, I think, than the old one, and I hope to eventually also make this publicly available, not in the very distant future. In this context of massive parallelization, I also want to mention another issue that one has to be aware of, and Jim Stone already alluded to this, the limitations, of course, of floating point arithmetic on a computer. It's something totally obvious, and we basically all know about it, that there's a machine epsilon, and we have round off, and so on. But sometimes when you get problems due to round off, it gets a bit fuzzy. What the heck is going on, and how bad can really the errors be to the round off? Is it a bug, or is it round off? And so it's really, I think, useful to be really aware of what floating point mass is actually doing, and what the limitations are, and what side effects you can get that are sometimes undesired. Also in side effects that impact parallel calculations. Of course, on a computer, we represent real numbers with floating point representations, and these floating points, so here's a single precision variable in 32-bit, and double precision would have 64-bit. They have a mantissa and an exponent. And since you can only represent, in say 32-bit, there are only 2 to the 32 possible numbers. So that certainly is the maximum number of reals in single precision that you have. So the space of representable number is finite. It's a discrete set. And all your calculations are operating in this discrete set, right? And in particular, this means whenever you do a mathematical operation or any calculation, you're just adding or multiplying two numbers, you get a new number, and that new number must be represented in that set, so it's rounded to the nearest one, and you get the round-off error, and that's the machine epsilon. But the machine epsilon, that's what we all know about. But one other side effects of these operations is, for example, that certain mathematical laws that we take for granted don't hold any more than in this space of floating point math. For example, the law of associativity for additions does not hold anymore. Holds only approximately. Sometimes you're lucky and it holds exactly, but in general, if you have three numbers and you'll add B and C first and then A, you get a different result if you add A and B and then C. And so sometimes just by changing the order, depending on how these numbers, what the values are, you can get very large errors. And in one way, and in one version, in the other, the error can be smaller actually, substantially. And if you know about this, then it's of course useful to exploit this. And for my particular tree algorithm, this particular effect has this important implication, namely that it makes the results of your parallel calculations depending on the number of processes you use. And that's a nasty property. So ideally, you would like to have that your results are the same, independent of how many CPUs you use for parallelization. And for some parallelization algorithms, you can achieve that. For this way of the tree algorithm, you can't achieve that. Why? Because the way the tree forces are assembled, we basically have here partial trees on different processes, and that means that any given force on a particle will be the sum of individual particle multipole interactions. So you have partial forces for a node and a multipole that's represented here by these circles. And in one situation, say you have a given number of processes that you put on the problem, maybe 8 or 16, then a certain particle will get a force calculation like this, has a certain number of terms that are summed up, but the sum is carried out in part on different numbers of processes. So this first, there will be a tree walk along this partial branch, another process does walk this branch, another this branch, and you get three partial forces A, B, C. They will have to be added up to the total force. That's fine. And then in the situation B, you have a different domain decomposition because maybe you use half the number of processes. So now the tree walk is a bit more extended. You get a force here A prime and B prime. And of course, mathematically, actually you can guarantee that's the case in Gadget 2 that these little circles are all the same numbers, exactly. They are all the same reals. But they are now summed up in slightly different ways. And actually that makes A plus B plus C on the computer not exactly equal to A prime plus B prime. Bummer. So what this means is now that the forces will differ in their round-off depending on the number of processes. And that's enough for the chaotic nonlinear n-body simulations that you will find that individual particles actually follow or end up at different coordinates then. Just because of that round-off. That's sufficient to do this. So because these small perturbations due to round-off are amplified very quickly. This is partially a result of sort of the chaotic nature of and highly nonlinear nature of nonlinear collisionless systems. It's also a consequence of the tree calculations that where the force errors, I told you that one typically gets random force errors of fractions of a percent or so. But these force errors, they depend discontinuously on the particle coordinates. Because it can happen that you perturb a particle, then it suddenly crosses the boundary where now one particular tree is now opened instead of used as a multipole. And if that happens, you basically get a glitch in the force error. At that point, it jumps to a completely uncorrelated value. And that will put the particle off track. So basically, you diverging the Lyapunov exponent you're diverging even faster than exponentially normally, because you get these discontinuous jumps in the force errors once you have round off that differs between different calculations. So the final result of runs carried out on different numbers of processes in n-body simulation usually depends on the number of processes. By the way, this is also quite common if you change the compiler, if you change the optimization settings, because the compiler will rearrange some of the floating point math you put, carry them out in a more efficient way, and then you also change the round off. So convergence in a collisionless simulation cannot be achieved on a particle-by-particle basis. That's not, at least not with this sort of approach. You will get basically chaos, or you get distortions in the orbits just from round off. However, and that's the funny thing, the collective statistical properties of the collision set, they do not change, and they do converge nevertheless. It's quite an interesting property. So what this means basically is if you do dark matter n-body simulations or stellar n-body simulations in the collisionless regime with such codes, parallel codes, and individual particles are really noisy traces of the dynamics. They are essentially meaningless. You only can talk about statistical properties of collections of particles.
So does it make sense to go to 64 bits if you can? Or that property just will...
It does. Well, first of all, one has to ask, is that problematic or not? Right? I would argue it's not problematic, because also for the reasons we discussed earlier, that the force field is anyway very noisy and Poisson-like. So you have fluctuating forces, and it is for that reason also pointless to trying to calculate the force accurately, right? So that the direct n-body simulation force, we don't need that force. We need only an approximation, and we need random force errors. And these sort of round-off issues that come on, they are pretty well represented by random effects. So that's just an insignificant perturbation. So it doesn't matter. So you can do, in fact, because of that, because relatively low precision is needed, you can carry out these calculations often in single precision, and you're still fine. But of course, you're better off with double precision. I would always recommend double precision, because I've suffered so often from nastiness from single precision, which is just usually not good enough for anything. But it's usually actually good enough for this, unless you have a very high dynamic range in the calculation. But of course, if you use 64-bit double, the round-offs are a lot smaller, and these effects are weaker, a lot weaker. And you actually, one other thing you can do is there are ways which I'm not discussing. So, you would still want to prove, for example, that your code is formally correctly parallelized, right? So because this feature has basically, the main issue is only of this, is that you can't use that equality to prove essentially that your parallelization algorithm is correct, right? You don't know, is that because I've made a mistake somewhere in the communication, or is it because of round-off issues, right? But then you can use other arithmetic. You can, for example, sum this up here with 128-bit double precision, or even with exact arithmetic, what I've done to validate that your parallelization algorithm is actually correct, right? Because all these individual reals, they are the same for technical reasons. Right? It's just the summation here in the Gadget 2 code. Yeah.
What are the statistical properties that converge? So you simulate.
Oh, yeah. What are the statistical properties that converge? For example, the density profile. So if you get a centrally concentrated object, you will get the same density profile. The mean velocity of a halo, the velocity dispersions. Essentially, the sampling of the distribution function converges in a noisy fashion. So once you average any quantity over a collection of particles, you get something that's going to converge.
Do you have the same problem for the SPH part?
Yes, you have it in a similar fashion. Yes. It's not quite as prominent there, but it's in principle you can have similar issues there. You can also, there are ways to get around this. So as I said, you can, if you make the sums invariant, which with some tricks, you can then get things that are invariant with the processor number, but it's expensive to do so. So I come now to the to the second half kind of my my lectures that were assigned to me, and that they deal with smooth particle hydrodynamics, and that's an interesting particle-based method to treat hydrodynamics in a so-called Lagrangian form. Lagrangian form because you're trying to move along with the flow, and your resolution elements are not fixed in space like in the Eulerian approach, but they are essentially pieces of the flow, and you translate along so these with this piece and follow how it's reacting to the forces from its environment and so on. And the Euler equations are the equations of ideal gas dynamics without MHD, so I do it much, I look only at a much simpler problem than Jim has described. So we're going to look only at the ideal gas dynamics of an inviscid gas. And here then the Euler equations of ideal gas dynamics in Lagrangian form look like this. And they are remarkably similar, also simpler than in the corresponding Eulerian form. Here you have a convective derivative, d dt. So this is the this is basically partial derivative plus v gradient operated on v. And that's the acceleration of a fluid parcel. And it is accelerated by the pressure gradient and by a gravitational field. So that's the acceleration equation. Then you have a continuity equation that just describes conservation of mass. And you have an energy equation, which is basically equivalent to the first law of thermodynamics, if you like. And that describes here the change of the thermal energy per unit mass. That's just the temperature. By adiabatic work that's done onto the fluid element or done by the fluid element when it's expanding against pressure forces. That's this term. And then sometimes this is not belonging really to ideal gas dynamics. This lambda here is a radiative cooling function or heating function. So this describes a coupling to the radiation field. We'll hardly talk about this. So normally this term is also absent. And then you have just these little terms, and you need the equation of state for an ideal gas. Looks like this, monatomic gas. So that's the equation of ideal gas dynamics. And now the approach in Lagrangian hydrodynamics is, or especially particle-based approaches, is slightly different from the Eulerian approach, where you discretize the space on a mesh to then solve the partial differential equations that you have in ideal gas dynamics on this mesh. So you discretize the volume. But the other alternative is that you discretize the mass, so the fluid itself, and you partition it into different mass elements. And that's in the Lagrangian approach. So there are different ways. Normally you would also have, at an initial time, these approaches might be the same. In the Lagrangian case, you would have the mass in some certain finite volume. And in the real sort of Lagrangian approach, you would follow how this volume distorts as time goes on. And so in that sense, there is always a mapping between the volume viewpoint and the Lagrangian viewpoint in the real scheme. But we are doing something even simpler. We will represent the fluid then by mass points or tracer particles. That's the approach that SPH takes. We will represent the fluid by a set of discrete tracer particles and try to follow then the motion that way. And conceptually it is very simple because we have already seen that there's an acceleration equation for fluid elements. So if we somehow can work out a reasonable acceleration equations of motion for these particles, we have an equation of motion for the fluid, and maybe this gives a good approximation to the hydrodynamics, and that's basically the central idea of smooth particle hydrodynamics. The principal advantages of this right away is that you can follow with this flows that are not subjected to special geometric constraints, especially they can freely collapse and expand and so on. And when they do that, for example, in a collapse, you would have just as these particles suddenly bunch up together in a much smaller volume, their density gets a lot higher, and that is going to be automatically achieved here without any mesh refinement or anything. In fact, this method with SPH will be mesh-free, so it's a mesh-free approach to hydrodynamics. And the mesh is always somewhat nasty bookkeeping device, especially if the density contrast suddenly changes all over the place. And that's what's happening, of course, in galaxy formation. That's why SPH, especially in applications where you gravitationally collapse by large factors, why it's very popular there. So that's already from the start the principal advantage basically of SPH. And so you can do relatively fancy calculations with SPH. I'll just to relax you a bit, I'll show you an example. Very old calculation I've done many years ago of a forming galaxy cluster. And let me fast forward this a bit.
How many years ago?
Oh, almost, yeah. Yeah. I think 2001, something like this. So this is a map here of the simulated X-ray emission, and here you have the dark matter. So this is now a calculation that follows with particles the dark matter and also the baryons. And since you have this particle-based representation of the hydrodynamics, it's very simple to combine these two classes of codes, right? We already discussed that you need, for such a particle-based scheme, you need a gravitational solver that can deal very well with strong clumping, can deal with all these particles. And if you have that the gas is treated with the same method, then it's also self-gravitating, then you have it's quite easy. That's why it's comparatively simple to write self-gravitating SPH codes coupled to dark matter, much simpler than a mesh code would be. Because in a mesh code, you have always two things. If you try to do the same problem with a mesh approach, you will have to represent the dark matter with particles, as we discussed. There is no other efficient method. You have to do this with the collisionless Boltzmann equation in a Monte Carlo sense. And if you have this same thing for the gas, then this is just a lot simpler compared to now having to do, say, adaptive mesh refinement also on top of this. So this is one of the reasons why this is so popular. So now how does SPH really work? The central idea is a technique called kernel interpolation. And that starts out from this convolution formula here. So you have some field A of R prime R, and you convolve it with some kernel function W. And this is basically a smoothing operation for if the W kernel has sort of a shape, is normalized to unity, and has this sort of compact Gaussian-like shape, then this is going to be a smoothing operation. Now the idea is that you use that to construct so-called kernel interpolants from the particle coordinates that you have. So you have here somewhere in space a set of particles, and known at the particle coordinates you have this field A, right? So this will be our values AJ. So we have now a situation where we know a field only at the particle coordinates, and we want to construct from this an interpolant, basically a function that is defined everywhere. And that's done with the kernel interpolant technique in SPH. The idea is that you take this integral and you recognize I can replace this differential volume element here with the volume associated with a particle, which will be its mass over the density. And then I can represent this essentially as a Monte Carlo sum, this integral, by plugging in the volume element here, this m over rho, the values at the various coordinates, and then the kernel evaluated at the particle coordinates. So this is a Monte Carlo kind of approximation of this integral, and that gives me the kernel interpolant value. This is the estimate now, sort of an average at coordinate I here of the values of the fields of these particles. And the smoothing then also takes out some of the noise that might exist in this field. It makes it smooth. And that's the very basis basically of SPH, because, and we can, for example, now use that to estimate densities by recognizing if you put for the field A the density itself, which you initially don't know, then these here cancel, and you're left with this formula for estimating the density with the kernel interpolant on the masses. So that's essentially one of the primary starting points in SPH, that you have some way to get to the densities based on the particle masses and coordinates. And there's another important aspect of that. This formula now can, in principle, actually this is not only the density at I, but you can evaluate this for any coordinate r. So you replace the I here with r, Ri with r. Then you can differentiate this, right? So suddenly you have an interpolant that's also that also can be differentiated, and that is something that you can then plug into the to derive equations of motion. Some words on the kernel. This is quite clearly should be normalized to unity. It is very important to have a compact support, mostly for algorithmic reasons. But if it doesn't, say if you would use a Gaussian, you would run into an n-squared bottleneck because all other particles would contribute to the sum, right? So if you have a compact support that becomes identical 0 with a distance larger than some finite radius, then only the particles inside this circle will contribute to the sum. That's what you want. You look at a finite number of neighbors around you to calculate these sums. You don't want that this involves all the other particles, because then you would be back to an n-squared algorithm. So that's why I need compact support. You want to have higher order of interpolation. So there are kernels of different order. This is very similar to what we saw in the particle mesh approach or PIC approaches. You want to have a sufficiently smooth and higher order kernel, and you can then show by Taylor expanding the interpolant that that the errors are of certain order. So this is, for example, second order accurate then for the density estimate. But you can in principle use kernels of still higher order. They come more costly to evaluate because they need to be broader, involve more particles, and some of the higher order kernels then also go negative. And these so-called compensating kernels, they are problematic because of this feature that they can go negative. So they are usually not used. There was for a while, 10 years ago, so still a lot of research being done in different kernel shapes. But nowadays, I think the community has settled down on using exclusively this sort of simple cubic spline kernel. And in practice, they're really similar to the gravitational softening. You have to put the softening, but the detailed softening shape is unimportant. And unless you if you take a reasonable SPH kernel, the details of the kernel shape are also relatively unimportant. So how do the SPH equations now look like? So you can, for example, take this kernel interpolant to construct a smooth estimate for the velocity field, like this. And based on this, you can then also construct things like the velocity divergence, because as we said, you can differentiate the kernel interpolant, so you can pull the nabla operator in and apply it basically to the kernel. What you differentiate is the kernel. That's also why it better be a higher order thing. But now comes an interesting feature. There are always different ways to write down such approximations to differential operators. So the divergence of the velocity field, for example, can also evaluate it in a different way, in a symmetrized way, namely. And that follows if you, for example, use this identity for the divergence, then you basically take the right-hand side of this and do something simple-minded like this. And then you find that the divergence at particle I can also be estimated like this. And here you have a difference formula that involves pairwise differences, the velocity difference of j and I. By experience, it turns out that these formulations give a much improved accuracy. And so that's why one usually always tries to find for, as representations of these differential operators, these sort of pairwise formulations. That's usually done. And then we can go to the Euler equations and see whether we can discretize them with this sort of kernel interpolant scheme. And so we basically then want to directly transform the partial differential equations to a set of ordinary differential equations this way. Now the density estimate is something that automatically, if you like, fulfills the continuity equation, because mass is automatically conserved. We have assigned the masses to the particles and let them stay fixed. And so you can't lose any mass. So actually one equation is already gone from the system, no continuity equation. And that gives us the pressure. And so all we have to care about is basically what are then the internal variables per particle. Well, we really have the mass is fixed. Then there's a velocity of the particle, a coordinate. And then we need one thermodynamic variable. That is usually the temperature, that is the thermal energy per particle. Then the total energy is defined. Or you can take, and I come to this, the the specific entropy of the particle. Any case, once you apply now to the acceleration equation, to the Euler equation, these kernel interpolants, you can derive this sort of equation of motion based on the discretizing the Euler equation. So it is leaving out the gravitational field for the moment, but that's simple. That would be just adding a gradient force here. And you see that again, we have here a pairwise summation formula, right? Where the pressure terms of around the particle I are contributing. This is the neighboring particle J. And then there's the gradient of the kernel function. And this sort of notation here, Wij, means, this is basically a kernel between particles at distance Rij between these two particles. And this overbar here means the kernel here has actually been symmetrized. Because one thing that is usually done is that these smoothing radii, sorry, I need to go back to this important point. The adaptivity of SPH is usually realized by setting this radius over which you do the kernel interpolation. You set it such that inside this kernel there's a fixed number of particles or a constant mass. So that's the standard approach. So what then happens is if the thing collapses, obviously if you have a fixed particle number, you will then shrink your kernel interpolations radius. And that's also, this radius is kind of a resolution scale of SPH. That means if matter collapses, the resolution will go locally up, right? It's automatically adaptive in that sense. But if two particles interact, say this particle interacts with a force with this particle, this upper particle might have a different radius, Hj. And then that causes a technical problem that you have to symmetrize the kernels because, such that the forces are antisymmetric and you fulfill Newton's law, second law. So that's basically done here, but it was indicated with this notation. And the first law of thermodynamics, or the internal energy equation, looks like this. So here you see work terms, the velocity differences are dotted into the kernel gradient. So this is basically the adiabatic work terms that you have. Now this is basically the complete set of almost of the SPH equations of motion. So I mean, can hardly be simpler than this. If you compare this to the partial differential equation we started out with, this is an incredible simplification. But there's one piece missing here, namely, if you actually, you need an artificial viscosity to capture shocks. And this for similar reasons as in the SUS code, that otherwise you will not dissipate kinetic energy correctly in thermal energy in discontinuous shocks that you then get. So the artificial viscosity is something that is implemented in SPH as a viscous force, meaning that, for example, like this, and it's artificial, you are free to parameterize this, and there's an artificial viscosity tensor pi here. And normally this for Neumann-Richtmeier viscosity or so, there are different parameterizations of the viscosity, very similar to what's used also in SUS. And this friction force is parameterized such that when a particle is rapidly, or a particle pair is rapidly approaching each other, then there's a repulsive force that tries to keep the particles apart. An extra repulsive force, that's why a friction force. And since the particles move together, if you have this extra repulsive force, the particles need to do work against that force. They will be slowed down. You take out energy out of the kinetic reservoir, and you stick that energy, exactly that energy you stick into the thermal reservoir. With this formula down here, the heat production rate must exactly balance the rate with which you slow down the particles, with which you decrease the kinetic energy. And then your scheme stays conservative in the total energy. That's what you do with the artificial viscosity. And then when you do that, then you can calculate also discontinuities and shocks. Here is a Sot-shock tube problem, as Jim correctly described, not a difficult test. This is sort of the minimum test you have to fulfill. And SPH can do such problems reasonably well. I mean, this is a simple Sot-shock. Here, the blue circles here are SPH results. But you can see even in this problem also some of the typical numerical issues in SPH. Just want to bring them to your attention. So here there is the shock here on the right. And the shock is broadened, first of all. You need several resolution elements in SPH to resolve the shock. But, so what? I mean, the shock is a bit broadened, but what's important is that the post-shock properties in this range are okay. So you achieve the right dissipation, just the right dissipation. And that's not too surprising because the jump conditions, after all, coming from the conservation laws, and these things fulfill the conservation laws of nature. But you get a bit of post-shock ringing. Here you see a bit of ringing that you can get rid of by putting more viscosity, and then you make the shock broader.
So what is the reason for the ringing? For quick you can do that here, measure dispersion to give you the ringing. But for SPH, what is the reason?
Oh, you also have dispersion relationships for one. So I mean, this analysis of dispersion, SPH is also dispersive. Okay, at some level, you can calculate dispersion relationships, but the ringing is also if you put no viscosity at all, for example, then you just get it's not unstable. The code will not blow up, but you will not dissipate the kinetic energy that should be in thermal reservoir, and so the gas is sloshing around and doing some wild things which are unphysical, right? And the artificial viscosity is actually introduced to damp that, to take out this kinetic energy and put it into heat. And it's a matter of the strength of the viscosity whether the ringing is completely suppressed or not. At that level, that small level, it's since I would say this is compared to other errors in the calculation totally fine at that level. But you could get rid of it by putting yet more viscosity, but then you of course damping out other motions more. That that's always the tricky thing about the artificial viscosity, that you apply it, but it's operating then somewhere in your flow, and you want it to be active only in the shock, but it's also present in other parts of the flow, and there your flow is then not inviscid anymore, so it's becoming somewhat viscous. The Reynolds numbers that you can resolve becoming very low because of that. And so that's a numerical compromise you strike. And there are schemes where people have time variable. So for example, you can make this strength coefficients in the viscosity, say this alpha here, you can make this time dependent. And so in that way, trying to put the viscosity only, somehow your code realizes that there's a shock happening, and then it cranks up the viscosity, and with some decay time it is then reduced again to a smaller value. So with these tricks you can improve this behavior a lot. But fundamentally it's for the same reasons as in mesh codes, that without viscosity, without shock capturing, you will get unphysical ringing there. Because the fundamental equations that we initially considered, they, as we'll see, they conserve entropy exactly. Right? So they don't not account for the fact that basically this fluid description breaks down in the shock layer itself. Right?
I can see very well what you're plotting in the third diagram, but why is there a jump after the shock?
Yeah, this one. You mean this thing?
Yes.
Yeah, I was coming to this. So this is the contact discontinuity here. Okay, so what I'm plotting here, on top we see the density, this is the velocity, this is the entropy, and that's the pressure here. So at a contact discontinuity, the pressure is constant, right? But the other quantities can jump, and the velocity can't jump, that's also continuous. Here you see, well, actually the pressure is supposed to be constant, but there is a little blip. Okay, you see this little feature here. That's basically also sort of an error. And that is a characteristic thing that happens in SPH at contacts with large density jumps. And that then also introduces this feature here in the entropy. So why this is there, I'll get to in my next lecture. This is one of the most important artifacts in SPH.
So in the end, the artificial viscosity is needed because of our inability to run the physical model to deal with this, right? Or even if you want to put a physical model for what is going on at the shock, you still need to add something.
Yeah, I mean yes, in a sense. I mean so in the differential form, like here, the equations are essentially, the way I think about it, they are essentially in the shock layer itself. And in integrated form, they're still valid, but in the shock itself, you have at some level, there is some microphysical viscosity, and that's not in the equations in that form. But you can put physical viscosity, then you have the Navier-Stokes equations, but even there you will have usually some, then even if you simulate honey or so, you can still have shock in honey. You will still then not get this right if you just put in an ordinary viscosity, because that's sort of in the normal, that would be appropriate for the normal flow. I mean, probably if you have the Navier-Stokes equations, then of course the ringing would be damped by the physical viscosity that you have in the flow. And that might then not necessarily mean, you might then not need an artificial viscosity or not such a strong one in that case. But so then, so actually before I keep going, so you see here the three waves that are important typically in ideal gas dynamics, rarefaction waves, and then the contact is here, and the shock. And at the contact, you see this blip structure. This blip structure, as we'll see, this is responsible for some unwanted effect, a surface tension in SPH, and that's responsible also for some of the problems in not properly resolving some fluid instability. So, and that's actually an interesting point. So lots of people think about SPH like, oh, SPH can't handle shocks. And I think that's a misconception. Actually, you can handle shocks actually well. There's no problem there. You broaden them a bit, but the contact waves are more of a problem. And that's, I think, actually where the fundamental problems lie in SPH. So one example of this here is an SPH calculation of a strong shock overrunning a dense cloud in a homogeneous background. So this will run again. Let me just stop this. So what you have here is on top, this is some background density of hot, thin gas, and there sits a dense cloud at pressure equilibrium inside. And then now it's hidden by a blast wave with Mach number 10. So that's sort of a primitive model for a molecular cloud that's, say, overrun by a supernova blast, for example. And then this shock wave, as you see, will overrun the thing, and there's now a complicated structure of various reflected shocks that interact with each other, Mach stem, and so on. You generate vorticity by the baroclinic term, and that sort of vorticity, these vortices start shredding these clouds apart, but the cloud is also accelerated now downstream. And you see one interesting thing, that from this cloud, you rip out a few little lumps of gas. It's very clearly seen here. So this is material that's obviously from the initial cloud. And there are little droplets here left. And what's quite interesting is that these droplets, they're not dispersed, right? They sort of stay around and are still coherent. That we'll see, this is basically the same effect, that the contacts around it have a small surface tension, and that surface tension holds these things together. So this was already some of the an outlook basically to my next lecture, that there are issues in SPH. There are also ways to ameliorate them, but we have to be aware of them. But we also have to be aware of the strengths of SPH. There's some good things about it, a lot of good things actually. One is that mass is automatically conserved. You have one equation less. It's convenient. Momentum is conserved, total momentum. Total energy is also conserved. And actually, it's also conserved in the presence of self-gravity. Accurately conserved in the presence of self-gravity. This is something that a mesh code will not do you that nicely. So, the conservative hyperbolic approach to solving the ideal gas dynamics on a mesh is conserving total energy to machine precision, but only if you don't have self-gravity. With self-gravity, it's much more complicated for various technical reasons, and you probably achieve most of the time good accuracy, but there's no guarantee anymore, which is a bit unfortunate. Also, angular momentum is conserved in SPH, which is, there can be angular momentum transport due to viscous effect, of course, but total angular momentum is conserved. There's also entropy is conserved, and I'll get to this point. The entropy is actually strictly produced by the artificial viscosity and by nothing else, which is also a problem. There is no entropy production due to mixing or advection, unlike in mesh codes. And so you have complete control about the sources of entropy in that respect, right? So you have to produce it, otherwise it's not produced. And that's also the reason why you need artificial viscosity. Or you produce it through thermal conduction, for example. It's another way to do that. And furthermore, it's geometrically flexible, can be easily combined with vacuum boundary conditions. There's no high Mach number problem. The high Mach number problem is the issue that especially in cosmological structure formation simulations, you often have flows that are initially very cold. For example, that stuff that rains onto a structure, cluster or so. So there's gas flowing in very deep gravitational potential wells, but it's initially coming out of, say, a void or so where it's very cold. So it's flowing with very high Mach numbers and then hitting something. You get very strong accretion shocks. And these high Mach number flows are sometimes problematic to treat very accurately. In SPH, this is such issues are unheard of. So this is basically the good news. But as I said, I will try not to only give you the good news, but also the bad news later on. There's one interesting way to derive the SPH equations, and that I'll discuss next, the variational approach. It's very important. This was an important improvement in the had happened in the last years, basically, last 8 years ago or so. And one aspect, if you go through the SPH literature, is that you'll find that many SPH codes or practitioners in the field, especially in the older literature, will use slightly different SPH equations. And you wonder, what's the correct form of the SPH equations? Well, in some sense, at least it used to be the case that this wasn't clear at all, right? Because you could come up with different ways to write down these equations. You would, for example, you would symmetrize these kernels in different ways. Some people would prefer to symmetrize the kernel by taking, say, the arithmetic average of the two smoothing lengths of two particles interact. You could also average the kernels themselves. Then you can also symmetrize the pressure terms in different ways. This is sort of the standard formulation. Then some people suggested to use the geometric geometric mean of these two pressure terms to have antisymmetric forces. And that, of course, raises the question, and a lot of experimentation has been done on that, is there a best choice really for this? And I would argue, actually, yes, there's one choice that's a lot more, much better motivated than on some of these more or less arbitrary choices. And one way to derive this is if you focus not on the thermal energy, but take more or less equivalently the entropy in a particle, or rather, so if in reversible adiabatic flow, you know that each fluid element will live on an adiabat, where the pressure is related to the density to gamma with some coefficient in front, which we can call the entropic function, A. And this is used a lot in astrophysics. If you go to X-ray, the X-ray community, if they plot, say, the entropy in a cluster of galaxies, so they will plot something like the pressure over rho to the gamma. That's simply called the entropy, even though this is not strictly the microscopic thermodynamical entropy, but the two are related in a one-to-one relationship to each other. So this equivalently is basically the entropy, this constant A. And it's much more convenient to work with, say, the Sackur-Tetrode equation or so, that this gives you the entropy of an ideal gas. So then the idea is to not integrate the temperature itself, but we integrate this entropy as the independent thermodynamic variable. And whenever we need the temperature, it's related to via the density, we can then calculate the temperature, U. And the artificial viscosity will generate entropy. So this would be the entropy production rate by the artificial viscosity. And if we do it like this, then actually we eliminate one more equation from the problem, because we simplify one equation a lot. So the thermal energy equation goes away because the entropy stays constant in adiabatic parts of the flow. So if there's no viscosity, entropy is constant. So these AIs are constant unless we have some artificial viscosity operating. So that's then the evolution equation for the entropy. And that's positive definite, so you can easily convince yourself will only grow with time. And then why is this now important? So this has been all known long ago, but Lars Hörnquist wrote a long time ago a paper where he pointed out that in these two choices, if you integrate the thermal energy, then the entropy conservation can be violated. What this means is that sometimes, if you integrate the thermal energy, this A coefficients will go down. Okay, so the entropy will decline, which is principle unphysical, and the sum of the entropies will not be conserved either. And vice versa, if you take the entropy instead, as I said, then due to discretization errors, actually the total energy will not, so it will be conserved in the continuum form of the equations, but not in the discretized form of the equations. And then, so there's no manifest energy conservation then anymore. And that was a big disadvantage. And usually people prefer to work with the thermal energy because it's more intuitive. It turns out the trouble is caused by this adaptive behavior of SPH, the fact that there are terms that are usually neglected in equations which have to do with the time and spatial variation of the SPH smoothing length. These are usually neglected in the SPH equations, and these errors, they stem from neglecting these terms. And so one can try to incorporate them. It's a bit complicated. It's usually not done. And then the question is basically, okay, if we neglect that, do we have to worry about these errors? And also, can we do better? And turns out, yes, you can actually do better. And you can work or derive SPH in a more elegant way, I would argue, from variational and Hamiltonian principles. For example, you can look at the Lagrangian of the fluid, or the Hamiltonian is also possible. So the Lagrangian would be here the kinetic energy minus the potential energy, and for the fluid Lagrangian that gives you the Euler equations, that's the thermal energy of the flow. That actually basically acts like the potential. In fact, in SPH, if you think about it, the thermal energy here on the right, if you assign each particle a thermodynamic quantity, the entropy, then the thermal energy is given by this combination of entropy and density. And the density itself is only a function of coordinates, right? So this is pretty much like a somewhat complex potential, right? So the particles move in this sort of thermodynamic thermal energy potential that they generate via their mutual density estimates. And so you can take this Lagrangian and just write down Lagrangian equations of motion. That are the SPH equations. So that's the discretization. But here you then come across one problem. You need to say, how do you set the SPH smoothing length, h, right? Because those also depend on the coordinates of the particles. And then, for example, you can incorporate this here with a Lagrange multiplier that you say that you want the mass inside the kernel volume to be constant. That's one way to do this. And if you do that, then you get the equation of motions with these Lagrange multipliers and putting in that constraint that way. You can also do it without Lagrange multipliers, but at the time I've done it that way. And then you arrive at this equation of motion in SPH. And now you see something interesting. So this is basically the standard equation of motion in SPH, except that the gradient terms of the kernel are now paired up directly with the pressure force. So previously one didn't know that that's the right way to do it, but this comes out of basically, so previously one put the kernels out here, out of the bracket, and symmetrize it there, but the symmetrization is basically best done by directly pairing this up. And in addition, there's a factor here in front, a little correction factor, which is this thing here, a partial derivative of the density, very simple to estimate along with the density estimate itself. And that's usually unity, unless you have strong spatial gradients in the smoothing lengths. So usually these factors are close to unity. But these are actually the correction factors that take into account these grad h terms, and they do that at all orders automatically. So you don't have them explicitly, but they're implicitly in these little tiny correction factors. And with that formulation, you can now show that both the energy and the entropy are conserved simultaneously. And you have no freedom anymore in the SPH equation. So there's one, in quotes, exact way of the SPH equations if you start in that sort of, from this fluid Lagrangian. And it's indeed the case that actually this formulation gives better results for test problems. I'll just show you for an example. This is at very low resolution Taylor-Sadov blast wave test where you have a three-dimensional grid of points. Only one plane is here shown, and you inject a lot of energy in one of the particles, a lot of thermal energy, and the rest of the particles is cold. That gives you a point explosion, and you get a Taylor-Sadov blast wave, a self-similar shock wave that runs out of this and piles up a lot of the matter in the shock wave. So that you can, for example, use to compare to analytic results. And at low resolution SPH, if you look at the profile of this, the density structure around the explosion site in 3D, then you get something like this. So this is, at low resolution, you see here the individual particles. It's the black triangle. Some average is the red here. And, the real analytic solution for this problem is this spike here, right? And this is a self-similar thing. This will just run out like this. And, okay, I mean, you see that, well, there is a density bump here where we should see the shock spike, but of course the peak density is quite far off from the maximum compression of factor 4 that you have here. So this is based in infinite Mach number shock here, because this is arbitrarily cold in the upstream regime.
How do you improve this? If you add more particles, you get...
Yes. So you can go, I'll show you later, you can go arbitrarily, well, it gets more cost and cost. You can go up here by having better resolution. So you see basically that the shock is broadened heavily, okay? And you also have, what's interesting, you have, you see here up front, you see already that the shock, where the compression starts due to broadening is ahead of the shock, right? And that also, by the way, means that there's entropy production ahead of the shock. Now the geometric scheme is much worse, right? So this was when you symmetrized the pressure forces with the geometric mean. You see that now the shock is, you have serious timing errors and it's much more noisy. And that is now with the entropy scheme. This is a bit better. You see that there's less noise than in a normal, and you see it maybe better if you look at density cuts through the shock wave. So these are different SPH formulations, and overall this sort of entropy scheme does best. And you see this also in many other problems that it does better. Actually, sorry, I thought I had a resolution test. But I can just assure you, if you do with higher resolution, you get closer. But it's at low resolution, it's looking like this. Yeah. That, by the way, is also, if you do this at low resolution with a mesh code, you will also initially not recover that. Right? It's not actually very much better than this.
Does it change if the particle distribution is not Cartesian?
It changes in this. Well, you will have more. So if you do it with a glass-like distribution, you will see a bit more noise because it will not be so spherically symmetric, or there will be more irregularity depending on. You might see in residual structure from the initial explosion site. This also depends then how do you actually inject the energy. They say if you do it with a single particle, this is in some sense not consistent with the SPH formalism, right? So if you put it like a top-hat SPH kernel energy in a glass, then you get good result, much better result. But for a single particle, you might get slight asymmetries early on and so on. So that is, you see now. But these are good tests. When you do this, you see some of how the scheme reacts when you treat it badly. Basically, that's what you should do. Where this really is important, however, is what I mentioned before, that the issue of entropy non-conservation and conservation. When you have a radiatively cooling flow with SPH, which is basically the extremely important application of this in structure formation calculations, say you form galaxies or groups of galaxies, and you have gas here, which is shown here in projection, and radiative cooling, the gas will cool and assemble in the centers of these galaxies and then become available for star formation. And a goal of cosmological simulation is, of course, to estimate accurately how much gas becomes available for star formation. And if the standard answer is a lot, and there's a overcooling problem, and the question is it completely physical, or is there some part of it to numerics also? And here we found at the time when we analyzed this that actually in the standard SPH formulation, because in poorly resolved flows, in cooling flows in particular, you don't accurately conserve entropy, and you actually from that get an excess cooling. You see this if you compare low resolution, high resolution cooling flow simulation in these galaxy clusters. This is sort of some measure of the entropy change of the particles with time, and if you do it with the thermal energy, you get much faster and excessive entropy loss compared with the entropy integration. And the fact that this is really wrong, you see if you do it with high resolution when the two schemes agree, and you see that this effect is a low resolution effect in the standard algorithm that you then get due to conservation errors in entropy. You get spurious additional cooling, basically. So that's where things like this come really into play. Now, finally, a few minutes I have on algorithmic aspects of SPH. So the crucial thing is to find neighbors quickly. That's what's setting the speed of an SPH code. And there again, if you have a gravitational tree code, you can reuse it for finding the neighbors. And that's working like this, that you do a range searching technique. So if you, for example, want to find the neighbors around this particle, you look whether your search region overlaps with the root node of your tree. If it does, you have to open this tree node because there's an overlap. And then you look at the daughter nodes where there's an overlap. And you keep going like this. You just open always the nodes where you see an overlap. And that way you find very rapidly basically your particles. So that's how you can use the tree. There's one additional complication here that we need for the force law. We actually need, we don't, in a sense, we don't know this radius up front. This is the radius hi of the particle I. But we actually interact here with all particles j for which this condition holds. So it could be that there's another particle j over here which has a large search radius which still encloses us. Then we need to be able to find this as well. And then some codes use just a guess and say, oh, okay, let me look in. I just look randomly in twice as large a search region and so on. But that's, of course, an unsafe procedure because you're not guaranteed that there's not another particle somewhere else which has a huge radius which still sees you. How do you find this efficiently? Well, you actually store for each tree node the maximum of all smoothing lengths of the particles that are contained inside. If you know that, then you can change your opening criterion such that you will open all the nodes where there is still a chance that they contain a particle that overlap with you. And that's then the very elegant way to do that. So I think I'm exactly at 10:30. And so I would then move on next time to discuss a few implementations of non-standard physics, how you do this in SPH, and then move on to some examples and defects in SPH and so on. Thanks a lot.